Okay, so the next thing that we have here is a couple more examples related to the exact same concept, theoretical probability or classical probability also called. So example number 5 is two players Sangeeta and Reshma play a tennis match. It is known that the probability of Sangeeta winning the match is 0.62. So Sangeeta's probability of winning is 0.62. And so what is the probability of Reshma winning the match? So since basically Sangeeta's probability of winning the match is 0.62, that means that basically the rest of the chance is given to Reshma for winning. So Reshma's probability of winning would be basically 1 minus 0.62, which is equal to 0.38, right? In other words, you can say that Reshma's or Sangeeta's probability of winning is Sangeeta's probability of winning is Reshma's probability of losing. That you can say as well. But basically, this is also a case of complementary events, meaning that for somebody to win, somebody has to lose. So those are complementary events. So that means that then basically we said that, for example, you could say P of E1 plus P of E2 plus P of E2 is equal to 1. Now if I take this now I want to play with these words a little bit, but it seems that I can't right now. Let me open my window. Okay, so for example, in the case of the numbers, for example, when we throw a dice, what happens is that all the possible outcomes of this experiment are 1, 2, 3, 4, 5, and 6. So then, for example, if I define an event here, E1, call it E1, and say that, for example, let's let E1 be, for example, the event of getting all the numbers greater than 4. Let E2 be, for example, the event of getting all the numbers less than less than or equal to 4. So as you can see, this basically these two events, these two numbers occurring would basically be a part of E1, meaning that these are favorable to E1. 5 or 6, any of them would be favorable to E1. And then 4, 3, 2, and 1 are all favorable to E2. and E1 and E2 are complementary events. These two are basically complementary events. So as you can see, when you have two complementary events, then basically those two complementary events basically they cover all the different possible outcomes of a single experiment. Okay. Now let's go back to the example that we had up here. In the example that we had up here, this is about winning and losing. Winning and losing. So the concept of winning and losing in a match, one player has to win, one player has to lose, right? So that means that basically when I say in a tennis match, for example, Sangeeta's probability of winning, then the complementary event to that event, if I call this, for example, E1, then the complementary event to that event would be basically Reshma, basically, of course not, the probability would not be there. If I want to talk about only the events happening here or occurring here, I would say, for example, Sangeeta winning the game. Sangeeta winning the game, and for Sangeeta to win the game, Reshma has to lose the game. Reshma has to lose the game. Reshma losing the game, right? Now, so if I call this the event of Sangeeta winning the game and the event of Reshma losing the game, if I call this, for example, E1, and if I call this, for example, E2, now if I know that basically the probability of Sangeeta winning the game is 0.62, P of E1 is equal to 0.62, then since these two are complementary events, then P of E2 has to be some value A, right? It is some value A. And again, since E1 and E2 are complementary events, you can say that P of E1 plus P of E2 is equal to 1. That means that 0.62 plus A is supposed to be equal to 1, which means that A is equal to 1 minus 0.62, which is equal to which is equal to which is equal to 0.62, so that's 0.38. So now, since 0.62 and 0.38 add up to 1, that means that these two events are supposed to be complementary events. Now let's see if that logically actually makes sense as well, because sometimes you say something and it's logically not correct, especially when it comes to the complementary events. We have not defined that properly yet, so I might actually be wrong here about, for example, about choosing this word properly. So I said that basically 0.38 is the probability of is the probability of the event of Reshma losing the game. Is the Reshma's probability of, and this over here I have written winning the game, the same number. So one of these has to be correct and one of these has to be wrong. So let's see which one is correct, which one is wrong. So what that means is that if I say that if Sangeeta's probability of winning the game is 0.62, then Reshma's probability of winning the game is 0.38. This makes sense, right? And if I say that no, this doesn't make sense, right? This doesn't make sense. So what you can, I mean, based on logic, I can say that, so since Reshma's probability of winning the game would be 0.38 and Sangeeta's probability of winning the game is 0.62, then you can say that these two are complementary events, meaning that the complement of Sangeeta winning the game is Reshma winning the game. Although, again, if you want to think about it, probably it wouldn't make sense, but logically it is correct. So now let's take a look at the solution here. It says that let S and R denote the events that Sangeeta wins the match and Reshma wins the match. So S and R, right? So both of them, Sangeeta winning the match and R denotes the event that Reshma wins the match. So the probability of Sangeeta's winning is P of S. P of S is equal to 0.62, and which is basically given. And so the probability of Reshma's winning, which is P of R, is equal to 1 minus P of S, which is equal to, as the event R and S are complementary. Okay, if you want to think about it logically, you would say that as I did, logically you would say that Sangeeta winning the match, complementary to that would be Reshma losing the match. But it's not correct. It's the correct way of saying that, as far as basically complementary events go. Basically, these two would be complementary events, meaning Sangeeta winning the match and also Reshma winning the match. These two would be complementary events. So 1 minus P of S, which is equal to 1 minus 0.62, which is equal to 0.38. So you need to be careful about, because sometimes you think about something logically, right? But sometimes just logic seems to be right, but it is not. So you have to be careful there. And of course, as I was using my logic, I was aware that I might be wrong. So question number 6 is Savita and Hamida are friends. What is the probability that both will have different birthdays, the same birthday, ignored a leap year? Now, I'm not very familiar with the concept of leap year and that sort of thing, but let's see if we can find out what that is. So Savita and Hamida, basically two persons are friends. What is the probability that both will have different birthdays and the same birthdays, and ignoring the leap year? So if I ignore the leap year, So if I ignore the leap year, meaning that then I can take a year as 365 days. So then I logically I don't even have to be familiar with the leap years. So what that means is that now I have Savita and Hamida. They are friends. What is the probability that they will have different birthdays? The probability that they will have different birthdays. Different birthdays. Okay, so to solve this problem, so if I assume that basically assuming that basically Savita and Hamida have different birthdays, so assuming that Savita and Hamida have different birthdays, so let me start with the probability. So the probability, or basically P of, so if I take, let me actually take an event over here, because that way we can calculate that better. So let's call for example E1. Let's define as the event that Savita and Hamida have different birthdays. Right? So then I can say that P of E1, the probability of the event E1 happens, is basically all the different outcomes favorable to this divided by the total number of outcomes of the experiment. So the total number of outcomes of the experiment is that you know that there are 365 days in a year. So I can take this as all the different outcomes of the experiment, right? Now, if Savita and Hamida have different birthdays, that means that for example Savita, let's say that Savita has been born on for example on January 1st, right? Now if Hamida has also been born on January 1st, this is not favorable to this event, right? Except for that, any other day would be favorable to this event. That means that I can take all the 365 days of the year, and just subtract one from that, which means that I can take that as 364 divided by 365. Now, now the next part of this question is, so you can calculate this. For example, you can calculate it to be 364 divided by 365 as 0.997, for example. 0.997, right? Now, now the second part of this question is the same birthdays. So what is the probability? What is the probability that Savita and Hamida have the same birthdays? Have the same birthdays, right? So if I call, based on this question, I can define some event, for example, E2, and I define the event E2 as the event that basically that Savita and Hamida have the same birthdays. The same birthdays. And so if I want to calculate the probability of this event, I need to count all the possible outcomes of the experiment, whose number is 365, because I have 365 days in a year. And in the numerator, I have to count all the different possible outcomes of this experiment which are favorable to this event happening. So what that means is that now the event is that the two persons have the same birthdays. That means that if Savita has been born on January, for example, 1st, then Hamida must have been born on the same day, on the exact same day. So, but now this day can of course change, because this is something hypothetical. I don't know when Savita was actually born, but I know that whatever that day was, which was only one day, it can be only one day in a year, then Hamida must have been born on the exact same day of the year. So so there is only one day that is basically favorable to this event. So I can write this as 1 divided by 365. So 1 divided by 365 is the same thing as 0.003. Rounded to 3 decimal places, that would be 0.003. And these two events are complementary. These two events, E1 and E2, are complementary events. E1 and E2 are complementary events because basically P of E1 plus P of E2 is equal to 0.997 plus 0.003, which is equal to 1. Of course, we have never proved this, that if the sum of, for example, if the sum of the probabilities of two events is equal to 1, then those two events are complementary. But I think, I'm not sure. Of course, I am sure, but we have never proved this. And there is one more way to tell that the two events are complementary, because as you can see, the two events they do actually cover all the 365 days of the year, meaning that for example the first event over here. Now suppose that Savita has been born on January 1st. So if I'm thinking about the event one, that Savita and Hamida have different birthdays, then that means that basically the event basically favorable to this event would be January 1st. No, I'm sorry. If I'm saying that if the event that we are talking about is that Savita and Hamida have different birthdays, if they have different birthdays, what that means is that if Savita has been born on January 1st, then Hamida has been born. So the first event is that Savita and Hamida have different birthdays, right? So that means that if Savita, for example, has been born on January 1st, then Hamida could have been born on any other day of the year except for January 1st. And so you have 364 days over here favorable to this event, but not January 1st. So there you have 364 days of the year basically favorable to this event. Now over here we said that basically E2 was the event that Savita and Hamida have the same birthdays. Now we said that Savita was born on January 1st. If Savita was born on January 1st, and they had the exact same birthday, that means that Hamida was also born on the same day. And so January 1st which is only one day of the year, is favorable to this event. And so there you have one day, and there you have 364 days. So you have all the 365 days of the year completely covered. That means that E1 and E2 are actually complementary events. So that is that. So we have a couple more questions here still to cover. Okay, so the next question that we have here is example number 7. There are 40 students in class 10 of a school, of whom 25 are girls and 15 are boys. So you have 40 students. From these students, basically 25 girls and 15 boys. And 15 boys. Now the class teacher has to select one student as a class representative. She writes the name of each student on a separate card, the cards being identical. Then she puts cards in a bag and stirs them thoroughly. She then draws one card from the bag, and so that means that all of these 40 students have been basically put together randomly in a bag, and then they draw a card, meaning that one of these 40 people is going to be drawn. Of course, this is a random draw, and the situation is completely fair, and meaning that it's not going to favor any of the 40 students. There is no way to know which card represents which student, and so on and so forth. We just pick a card at random. So now, what is the probability that the name written on the card is the name of a girl or of a boy? So basically we have two questions here. What is the probability? What is the probability that the name written on the card, that the card basically represents, that the card represents number one, a girl, and number two, a boy. And of course you can see that these are so basically to answer the first part of the question, what's the probability that the card represents a girl? So I can basically, based on the first question, I can, for example, I can basically define an event E1, and I can call it the event that the card represents a girl, right? So the event that the card represents a girl. Now the probability of E1 is going to be basically all the outcomes of the experiment that are favorable to E1, which is basically we know that we have 25 girls here. Any one of them is picked, it's going to be favorable to this event, because this event simply says that the card must represent a girl. It doesn't matter which one of the girls. Is just the only thing that matters is that it has to be a girl. So over here we have 25 outcomes favoring this event E1, and the total number of the outcomes of the experiment is 40, because we have 40 people in total. So 25 divided by 40 is equal to, divide by 5, you'll get 5, divide by 5, you'll get 8, 5 eighths. So that is equal to 5 eighths. Now, for basically part 2 of this question, I'm going to again define an event E2, and I'm going to call it the event that the card represents a boy. And to calculate basically the probability of that event, I need to divide all the outcomes of the experiment that favors E2, or favors this event, which is 15, because this event tells that basically the card must represent a boy, and I have 15 boys over here. And the total number of basically outcomes of the experiment would be 40, because in total I have 40 students over here. So divide by 5, I'll get 3, divide by 5, I'll get 8, so that's 3 eighths. And as you can see, basically, since these are the only two outcomes of the well, you could say that these are also complementary, because you could say that basically you could say that, for example, the probability of the event that the card represents a girl, if you say that the probability of the event that the card represents not a girl, that would be a boy. And there are only these two sorts of outcomes in this experiment. So it's really enough to basically calculate E1 and then or P of E1, and from P of E1 then you can calculate P of E2, because as you can see here, P of E1 plus P of E2 is equal to 1, which means that 5/8 plus 3/8 is equal to 8/8, which is equal to 1. So that's basically question number 7. Now I'm not going to call it complementary or anything because I'm not really sure about the definition. I don't want to unnecessarily give us wrong information, so just leave it at that. Now question number 8 is example is a box containing 3 blue, 2 white and 4 red marbles. So you have in a box you have 3 blue marbles, you have 2 white marbles, and you have basically 4 red marbles. And you have 4 red marbles. If a marble is drawn at random from the box, what's the probability that it will be white or blue or red? So you can say that the probability of, for example, blue is basically all the favorable outcomes favoring basically favoring this event, which would be 3, because I have 3 blue marbles here, and the total number of marbles is 3 plus 2 is equal to 5, 5 plus 4 is equal to 9, 3 ninths, which is equal to 1/3. The probability that the marble will be white, for example, is basically 2 divided by 9, and the probability that it will be red, or P of red, is going to be basically 4 divided by 9. Now if you add all of these probabilities together, you'll get 1/3 plus 2 ninths, for example, plus 4 ninths. Take LCM as 9, 3 plus 2 plus 4, that's equal to, that's not supposed to be like that. 3, 2 and 4, 5 plus 4 is equal to 9 ninths, which is equal to 1. So these are all the different, basically all the possible outcomes of this experiment. Add the probability of all of them together, you'll get a 1. Or you could say that basically P of blue plus P of white plus P of red is equal to 1. Now the next question that we have here is Harpreet tosses 2 different coins simultaneously. So what Harpreet is tosses 2 different coins. 2 different coins simultaneously. 2 different coins simultaneously, and that's basically 2 different coins. For example, let's say a 1 rupee coin and the other was a 2 rupee coin. What's the probability that she gets at least 1 head? Okay, so in this experiment, it doesn't really matter if the coins are different or not, because these are, you can say that these are just 2 coins flipped or basically tossed at the same time simultaneously. And if I call them, for example, coin number 1 and coin number 2, the first coin and the second coin, so the first coin could have 2 different outcomes, either heads or tails. the second coin has the same two different outcomes, the heads and tails. So that means that if I take, for example, I can take these two, take a combination of these heads and tails together, meaning that I can have, for example, heads with heads, heads coming from here, heads coming from here, heads and tails, heads and tails, heads coming from here, tails coming from here. I can have tails and heads, and I can have tails and tails. So these are the four different outcomes of this experiment, tossing two different coins simultaneously. So in total I have four different outcomes. Now, what is the probability? What is the probability that she gets at least one head? That she gets at least one head. So at least one head means that you get one head, but you could get more than one head. Meaning that, for example, this would be favorable to this event. For example, if I write this event E1 as basically she gets at least one head, or one heads, basically. These are heads. At least one head, so you would have basically this would be favorable. This what do you call it? This would be, well, whatever that is called. I don't get the word right now. This would be favorable to E1, this would be favorable to E1, this would be favorable to E1. And it doesn't really matter based on the way that the question has been asked. It doesn't matter which one gives you the head, so it could be from any coin. So that means that you have 1, 2, and 3 events, or not events, but you have 3 outcomes favorable to this event. So that means that P of E1, you can write it as 3 divided by the total number of outcomes, which is 4. So the probability that she gets at least one head would be 3/4 or something around, I suppose, 0.75 or so. But then let me see how they have solved this problem. It says that we write H for head and T for tails. When two coins are tossed simultaneously, the possible outcomes are these, what I have written over here, which are all equally likely. So I can write here which are all equally likely. This is the assumption that we made in the beginning of this chapter, which are all equally likely. So here heads and heads means heads up on the first coin and heads up on the second coin. Similarly, heads and tails means heads up on the first coin, tails up on the second coin, and so on. So now the outcomes favorable to event E, at least one head, are these three outcomes. So the number of outcomes favorable to E is 3, so you get P of E is equal to, or P of E1 is equal to 3/4. That is the probability that her peach gets at least one head is 3/4. And there is a note here which says that you can also find P of E as follows, meaning that you can get P of E. Let's call this event, for example, denoted as E. Then P of E could also be written as basically 1 minus P of E bar, which is the complement of E. Now the complement of E, when you say at least one head, the complement of E would be getting no head, right? Getting no heads basically. So that means that P of E bar means 1 minus so that means that if P of E represents the probability of getting at least one heads, what that means that then P of E bar, which is the probability of the complement of that event, that is basically the probability of getting no heads, right? Because if I take E as the event of getting at least one head or one heads, then E bar, which is the complement of E, means the event of getting no head, right? Now basically the event of getting no head, now if I calculate P of E bar here, the probability of getting no head would be basically only 1 out of 4. So I have 4 outcomes here and only 1 would be favorable here. So then using this relationship, I can say P of E is equal to 1 minus 1/4, which is equal to basically 3/3 minus, this is 1/4, I suppose. 1/4. 1 minus 1/4, which is the same thing as 4/4 minus 1/4, which is the same thing as 3/4, which is what we have calculated here. So now there is some text here that says that did you observe that in all the examples discussed so far, the number of possible outcomes in each experiment was finite. The number of all the outcomes, or the number of possible outcomes in each experiment was finite, which is of course something you would, I suppose you would agree with. Now there are many experiments in which the outcome is any number between two given numbers, or in which the outcome is every point within a circle or rectangle, etc. Can you now count the number of all possible outcomes? As you know, this is not possible since there are infinitely many numbers between two given numbers, or there are infinitely many points within a circle. So the definition of theoretical probability, which you have learned so far, cannot be applied in the present form. What's the way? How can we basically all of the situations that we have that we've had so far, they were all about the kind of situation where the number of possible outcomes were basically finite. We could count them. But for example, in the case of a circle, suppose that you want to find the number of points, for example, between 2 points on a circle. So then, of course, you know that the number of points between those 2 points is infinite. Or suppose that you want, for example, to get the number of numbers between two definite numbers. Even in that case, you know that there are an infinite number of numbers between any two numbers. So in such cases, we have a way out which I don't remember what that was, but we can find out. We can find out. So let's discuss this as well in this video, and then after that we will basically end this video. Okay, so now in order to understand that procedure, and I have read this before, but I don't remember it really. Let's see what this example is. The example says that in a musical chair game, the musical chair is basically, they put a bunch of chairs around, and then there is a bunch of people, and then somebody is in charge of music, and then they keep basically stopping the music basically randomly, and then you have to find the chair to sit. If you don't find the chair, then you have lost. That's the kind of game that is. So it says that in the musical chair game, the person playing the music has been advised to stop playing the music at any time within 2 minutes after she starts playing. So at any time within 2 minutes after she starts playing. What is the probability that the music will stop within the first half minute after starting? So the person is advised to, the person is advised to stop playing within 2 minutes after she starts playing. Within 2 minutes after she starts playing. And so now what you want to know is what is the probability that the music stops within the first half minute after starting. Within the first half minute after starting. Now the problem here is that if you basically, if I take an event, if I define an event something like E, meaning that defined as basically the music stops within half minutes of starting. And now if I want to calculate the probability of the event E occurring, what happens is that I have basically, I know that the music is supposed to be stopped within 2 minutes, meaning that at most I have 2 minutes here. And I know that the music stops within half minute of starting. So within half minutes of starting, that would be basically, if you take this as 0 minutes and 1 minute and 2 minutes, for example, This is 2 minutes. So half minutes would be over here. Half minutes would be over here, and then the problem is that there is countless points in time within t is equal to 0 and t is equal to 1/2 minutes. So there is no way to basically there is no way to know what sort of number to put here, because there is an infinite number of time points within this time interval. So now let's see what the solution is. It says here the possible outcomes are all the numbers between 0 and 2. This is the portion of the number line from 0 to 2. This is basically the possible outcomes. And let E be the event that the music is stopped within the first half minutes. The music stops within the first half minutes of starting. And the outcomes favorable to E are points on the number line from 0 to 1/2. So the distance from 0 to 2 is basically 2, while the distance from 0 to 1/2 is 1/2. Okay, so now so basically we said that the distance between 0 and 2, the distance between 0 and 2 is 2. So if you think of that as a distance, then there is a way to solve the problem, meaning that basically between 0 and 2, if I take this as a distance, the distance is going to be 2, meaning that I'm not thinking of this as a point in time. I'm thinking of this as a duration of time. So as a duration of time, it's going to be that the distance between 0 and 2 would be 2. Would be just 2 units over here. And the distance between 0 and 1/2, which is everything favorable to E, would be 1/2. So if I divide 1/2 by 2, I will get a 1/4. So the possibility that the music stops within the first half minutes would be 1/4, or basically 25%, because well, even if you think about it, so the distance, or basically 2 minutes, would be 1, 2, 3, and 4 times basically half minutes. So that would be 1/2 minute, another half minute, another half minute, and another half minute. And so there is a 25% chance that it stops here. There is a 50% chance that it stops here, 75%, and 100%. And 1 divided by 4 is actually 0.25, so that's 25%. So now we can extend this idea to example number 10 for finding the probability as the ratio of the favorable area to the total area of some land. That is also an interesting problem that we can do in the next video. And let me actually see how many examples are left. There is still a couple problems left here, so that we will do in the next video. Thank you.